again. Apologize for being away from Carmen for the past week. Actually, this was a kind of a bad week. I was traveling the first part of the week, and then had more firefighting to do in the latter part of the week than I'd hoped. Other than that, we're pretty much on schedule. I'll get the other remaining three lectures up pretty quickly. I want to start out today with some housekeeping, and then we'll get into the main topic today, which really is about the strength of metals. Dislocations. I think you're familiar with the idea from teachers camp that this is the way metals deform, is by motion of dislocations and plastic deformation of metals. And the theme we're going to hit with this is how we give materials strength. And there are some time-honored things that we do all the time to give materials strength, and you'll see that this relates directly to the phase diagram, directly to microstructure, directly to how we do processing. So again, this is really right at the heart of material science. And again, there's lots of demos that you can do that are part of sort of the ASM group of demos that support this pretty nicely. And we'll get into that in just a minute. First, what I want to do is there have been a couple projects come up. We're nearing the end, sort of, and I think there's actually another week I can deploy. I think I had said we'll button things up by like the 1st of March, and we can run out to the 7th or so very easily. But projects, basically, first of all, short statement of purpose on my point is, what I really want to do is give you guys resources, show you where you might be able to get some additional stuff regarding material science, some additional material, and then also you have to have some basis for giving grades. Basically, I want to give grades. I want to make this as painless as I can. I have sympathy for all of you. I know you're all doing other jobs while you're doing this, and but I know a lot of you are doing material science teaching also. So what I really want to do is show you where some resources are, give you the opportunity to answer some questions, and hopefully give you a little bit of depth you don't get in the course. So I'm going to be very, I'll interpret this in the most generous way that I can. So what I had in the syllabus to begin with was talked about 25-point projects and 45-point projects. And for each of these, what I would like to have ideally are three basic things: is a lesson plan that shows what you do, and ideally it's what you use with your students. Ideally, what I'd also like to do is have the permission to post this so that we can show other teachers what works. Some examples of student work, if you have that, and if you are able to do this, some reflections on what does or does not work. And I recognize that not all of you are teaching material science. I'm going to be lenient if you can put in any kind of a reflection paper of any kind of a plan of how you might approach your school board, anything that's at all related, I'm happy to look at. So again, I'd like to give good grades. We'll be lenient. So what I had in the syllabus is 25-point project is at least one activity from the teacher's camp. Show that you use it in class somehow, how you adapt it. Show some examples of student work, and then show some reflections on what does or doesn't work. And then basically, as a slight discount, but 45 would be to use multiples of these, and for at least 3 lessons. And other things, like I say, anything else that you want to think about how you might talk about engaging colleagues or engaging your school board or your administration, anything along those lines, I'm happy to do. Just feel free to make a proposal, and we'll pretty much do that. Okay, feel free to hit me on the discussion board or privately through email if there's any questions about that. So there have been a couple questions about the detailed rubric, and I feel if I try to make anything detailed, that's going to take a lot of the flexibility away from it. So ask me questions, but that's about as simple and straightforward a statement of purpose as I can give you on this. Secondly, this came up a couple of times: is how do you do this problems like this? First of all, in the lecture that you had up there, Professor Frankel put up an equation where he has a rate, and it was just an absolute mess of units. Rate, and this is in mils. In a mil is 1/1000th of an inch is equal to 534 times W, where W is given as a weight change in milligrams, and then he had rho at the bottom, which is in grams per cubic centimeter. Let me change the centimeter cubed. He had at the bottom also area expressed in square inches, and he had time expressed in hours. And this is sort of a big mess of units because you have mils per year, you've got inches over here, centimeters, grams, and just basically if you have the students in this area, it could be a pretty good thing. It's a nice little thing for doing units actually. So a milligram is and basically just put in units so that everything is equal to 1. We know that there's 1 gram per 1,000 milligrams. We're just multiplying that by 1. We also know that there's, and you'll see the grams on the top and bottom can cancel out this thing. With respect to centimeter cubed, we know that there are, how did it go? 2.54 centimeters per inch. So in centimeter is 2.54. Sorry, 2.54 centimeters is 1 inch. So I can put, to make it equal to 1, I can have 2.54 centimeters divided by 1,000 mils. This will help it work. You have to cube that. In terms of area, I can also multiply by this. So 1,000. Sorry, 1 inch per 1,000 mils, and that would be squared, and then time, it turns out in hours there's 1 hour. What are my notes on this? There's 8,766 hours in a year, and if you do that, the hours cancel, left with years. When you do this, you can come through and cancel all these units, and you'll end up being left with mils for a year, and that's basically where that 534 ends up coming from. It's a little bit of a nasty thing, but that's how you do that. Okay, that's a units problem. This was also a units problem that you had in the homework. This is a little bit easier to do. You just have a plate that has an 800 square centimeter area. In this case, there's a random number generator that makes these examples. 9 kilograms had corroded away. Assuming there's a corrosion rate of 6 millimeters per year, how long does it take to do that? You need to know the density of the material. So what we end up doing with this is the following, as we say that there's 9,000 grams are lost from 800 square centimeters. So what I have is I can figure out the thickness that is lost from that, and what I end up getting from that is I lose 1 point. I have to pull my calculator out. 1,000 divided by, I lose 11.25 grams per centimeter is what's lost. Then what I can do is take that, divide that by 4.5 grams per cubic centimeter, and we can see the grams go away and centimeters partially go away. That goes away. That becomes a 2, and I end up with 2.5 per centimeter squared. Actually, both as a centimeter squared there, so I end up with 2.5 centimeter material lost is what we end up getting from that amount. And then we know that this is going at a rate of 6 millimeters per year, so 2.5, or say do it in the same units, 25 millimeters divided by 6 centimeters per year gives you 4.1 years it takes to get that, and that's the answer that you end up getting there. And it's just a units problem. It could be a good one if your students are in that place. And what's nice about all this stuff is it shows real connections between engineering and real life. And the sad fact about most engineers is we do end up in this kind of dog's breakfast of units sometimes. You see all kinds of units put together, and then these nasty empirical factors that sit in front of that. That's something that you don't typically see at the when you're trying to deploy concepts like you do possibly at the high school level. But it is a useful skill, and it's amazing how many engineering exams you can actually pass just if you can end up working through these units. And I may not have done it real fluidly here, but if you keep diligent and keep the units there and keep hacking away at them, you can get this to work. Okay, let me get on and talk about the main part of this lecture, which is really dislocations, strength, and ductility. And things that we learned last time, are there a number of ways that we can figure out the number of definitions we can have for the strength of material. First of all, we can ask the question, is it stiff? We know that metals, for example, are much stiffer than plastics, and that's elastic modulus. We can ask how resistant are they to permanent deformation. That's what we're going to talk about today, is strength against plastic deformation. And then we could also ask how resistant they are to fracture, and that's fracture toughness. And metals turn out to be far more fracture tough than glasses. You can see that if you drop a metal plate versus a ceramic plate. There are different definitions of strength. What I'm going to talk about today is really how we give something plastic strength. So I give a piece of metal the strength so it won't deform permanently under load. That's what we're going to talk about. A simple demonstration I mentioned last time you could easily do to show this sort of thing is, for example, you could get some hardened aluminum, and you could buy this from McMaster Carr. McMaster.com, and you could look at what they call shim stock, and that's full hard aluminum. And you could do this like a diving board like this and see what the stiffness is. And what we end up seeing is that the stiffness of aluminum is about the stiffness of aluminum. It's about a third of that for steel, for example. And you could deform this, to some location, and you'd see that under, maybe you can see, you can see that maybe under a 10-gram load, for example, would deflect to a location like that and come back up entirely, and that would be the stiffness. Maybe under a 20-gram load, it would go twice as far. And what you could do then is take this material, heat it up with a propane torch, do this again, and you'd see that for the initial deflection where it comes back up, where it returns, you'd have the same stiffness, but you'd see that it takes a much smaller load to put permanent deformation in it. The material would be very weak, but it would have the same stiffness, again showing you that strength and stiffness are controlled by different things. And again, what we're going to talk about today is what controls strength. And strength is controlled by the motion of dislocations. We'll talk about what dislocations are first, show how that gets into strength, and then I'll mention a little bit about ductility, which we also mentioned last time, which is how far something can stretch before it breaks. And that's really important in manufacturing, is having something that's ductile. That's how, again, how you make something like a car fender or all kinds of things. The material has to bend in order to take the shape, and that's how we make inexpensive stuff, which we like automobiles. So what we're going to see is that the onset of dislocation motion is what really limits strength. We're going to see that we have time-honored strengthening techniques, and all of these work on basically impeding dislocation motion. And we'll also see that there are ways we can restore ductility, and that is make it so the material, the dislocations can move more easily, and that's usually done by heat treatment. And we'll see in here that there are a couple key vocabulary words, which we call recovery, recrystallization, and grain growth. And remember that metals are made up of crystals, so recrystallization is changing the size and shape of the crystals somehow is what goes on. So first of all, start with dislocation motion, and you probably could have pulled some of these up, but if you go into YouTube, you can find some nice pictures of this. And basically what we see is dislocations are line defects. So if you've got a bunch of atoms like this, you can imagine up above here, there's this extra half plane of atoms. Okay, that extra half plane ends at a line, and that line where the extra half plane of atoms ends is the line of the dislocation, because up here this looks like an absolutely perfect crystal, down here it looks like an absolutely perfect crystal, but right here in this middle area there's this imperfection, there's this line defect. Okay, and you can see the bonding isn't the same. These are all lined up along bonds, but there's this kind of dangling bond here. And what can happen if I put a shear stress on this, shear stress, talked about this before, is force over area. That'll tend to distort this. It'll tend to make this defect want to move this way, make it so that these atoms want to join with those atoms, and that could move this crystal defect off to that side. Okay, so if we put this shear stress on like this, it moves this defect, and it can cause to distort the crystal like that by moving the defect from this location to that location out to the end. If the dislocations don't move, you'll get reversible deformation that's just based on bond stretching. But if the dislocations do move, you get this permanent deformation, and you can see these offsets, and that's what causes the permanent deformation. Okay, as I mentioned briefly before, it's beyond the scope of this. There's a relationship between shear stress and normal stress, and here's, for example, if I take a zinc crystal, put a normal stress on it, stress is force over area. That can also turn into some shear stresses. You can see those offsets, and that's what we end up getting, and that's all the result of dislocation motion. So in this case, we're not going to spend much time at all on this in this class. This is what we call an edge dislocation, EDGE. There are also screw dislocations and very complicated dislocation structures you can get. Again, we will not even get close to scratching the surface of that. I mean, I've got good friends of mine that basically spend the better part of their careers talking about dislocations, and yeah, it's nerdy, but that's what we do. So anyway, stresses and dislocations in 3D, there's lots of ways you can get these shear stresses that happen from very simple loading conditions. And And you can see that the shear stress like this doesn't move that dislocation, but this component of shear stress, this force that's acting in that direction, will tend to put a force on that dislocation to move it in that direction. And in metals, dislocations just happen. When you solidify or process metals, you will always have a fairly high dislocation density. There's no way of getting around it. And you'll see in a minute that they can also they can multiply. You can get all kinds of additional dislocations that happen. So in order for the dislocation to move, you have to have the right kind of shear stress on it. They will move, and they'll move fairly easily. There's really nothing that stops them. It's very easy to kind of remake these bonds and have the dislocation move along, at least in metals. In ceramics and some metals, it's not quite as easy, but in metals, these can move. Things like aluminum and zinc, iron, so forth. Dislocations move actually very, very easily. So the trick is, if you want to make something that isn't going to deform permanently, what you have to do is make it so those dislocations will not move easily. And what we're going to do is talk in this lecture about the strategies that we use to impede dislocation and their dislocation motion, and therefore make high strength materials. So, and we'll put a couple equations behind this as well. So the strengthening strategies that we use, there are 4 that we'll talk about here, and there are some others out there that we won't talk about in this course, but the 4 we'll talk about here, first of all, is we can reduce grain size. And again, we know that metals and materials almost always are made up of these crystals that are fairly perfect, packed, and they fill space together. And this would be one crystal, second, third, fourth. Then you've got these intercrystalline boundaries that might look like that. And so when the dislocation comes along and hits this boundary, it's got to do something fairly special to reform itself and get on to the next material, into the next crystal. And it turns out the more of those boundaries you have, the stronger the material becomes. So the obstacle in this case is a grain boundary. The effectiveness of the boundary increases with misorientation. That's something we can't control very well. We can control the size of the grains pretty well. Misorientation pretty much just is what it is. And the smaller the grains we can make, you could these be large or small relative to the size of your component. The more barriers you have, the stronger the material is. And this is governed by something called the Hall-Petch relationship, where we can usually say the flow strength of the material is equal to some initial strength plus some constant K divided by square root of D, where D is your grain size, and that would be roughly that dimension there on a drawing like that. That would be your grain size. Again, that's one of those things that we can pick up and measure with metallography that we talked about already. That's also something we can control by how we process the material, by how we do the solidification, and we might do some of the mechanical processing. We control that grain size D. Okay. So the smaller D is, the larger this term is, therefore the larger the final strength of the material is. So we can, this is the same equation written slightly differently, and this is an example. This is a copper 30% zinc brass alloy that's shown there in the micrograph like we've talked about. And we can change these grain sizes, and you'll see a little bit later in this lecture mechanisms by which we can change the grain size. These are within this something called twin boundaries, these flat boundaries where you see contrast, and all that contrast comes about by basically polishing the material, splashing a little bit of etchant on it, and splashing is maybe a little flippant, but getting just the right amount of etchant on it the right way, you can pull those things out and then look at the optical structure of the material. And so here we see this term 1 over square root of D. Here you see the grain size here. This would be fine grains, medium grains, coarse grains. So you have small going this way, large going this way. Write large. And you can see as you go small, the strength goes up as it should. And this would normally be populated by, of course, real data points like that. Okay, so not too much more to say about that. The other thing that we get, one of the ways we end up controlling grain size somewhat, or controlling lots of properties within materials, is by rolling. And if you get Reynolds wrap, or the sheet that makes up, the sheet metal that makes up almost anything that you buy that's made up of sheet metal is made by rolling operation. A couple big steel rolls, imagine those are round, and you've got material coming in at one thickness, hits those rollers, and comes out a reduced thickness. Steel mills are full of rollers, so this would be the final thickness. This would be the original thickness. So if you've got a crystal in here that might be, imagine it starts out rather round. After it goes through this deformation, it's going to be more oblong like that. It's going to stretch in this direction and reduce in that direction. And you see that before rolling and after rolling. If there's nothing going on to kind of reform the grains as it happens, you'll end up with grains that have different directions. You can also have preferred crystal orientations in various directions, which is, again, beyond this, but it's something you can control. It's really quite a powerful way of controlling the structure of materials. So this material is something that we would think is isotropic, meaning that the properties are the same in all directions. And you can see these have a symmetric grain shape, random orientation. This material, just by looking at it, we can see is anisotropic, meaning that the properties vary with direction, and that can be a powerful thing if you use it right. And there's two sources of anisotropy. First of all, you've got elongated grains. Then secondly, you may or may not have preferred crystal orientations. But you can certainly see that there are elongated grains in that case. Again, that's something we can control and use with great power sometimes. So what we can do is, here's an example of how anisotropy can affect the material properties. This is a National Lab example of a tantalum plate. They roll it in this direction. This is the rolling direction. This would be the transverse direction. This is a width direction. They cut something out and they do something that's called Taylor anvil experiment. Taylor anvil experiment means that you fire this at something under speed something like 1,000 meters per second out of a gun, hits a rigid plate, and after it hits a rigid plate, it does this, looks from the side, goes and splat like that. And then if you look at the end view, you see that the material is basically weaker in this direction than it is in that direction. It doesn't splat out evenly. So that's what we end up seeing in anisotropy and deformation. That turns out it's just something you can see in real properties. It's always fun to be able to do experiments like that too. Okay, so that was the first one. That was grain size strengthening. The second thing we can do is, remember from our explorations of the phase diagram, we could make materials that had solid solutions of multiple atoms in there. Okay, so we can have big ones and small ones, copper, zinc, nickel, copper, all kinds of these sorts of things. And you can look up phase diagrams and see which ones, which things are highly soluble in others. So what we do is we can have the obstacle is basically an impurity atom. And so here's what the material looks like. We put a dislocation in it. You can see this is the end of this edge dislocation. This defect goes into the plane of your computer screen, goes back that way. But you can see that this is very crowded up here. And then as these planes come down, there's kind of some extra space here. So what you can do is you can have solutes that interact with this. And a couple of the solutes that you might be interested in would be, one would be a small substitutional atom that's smaller than average. Well, if you had a small substitutional atom, sits on the same lattice sites, where would a small one want to go in this picture up here? I'll probably want to go where things are really crowded, going to a spot like that. If you've got a large substitutional atom where it takes up more size than everything else, where might that want to go? Well, that one would probably want to go in a place like this where there's extra room. So if it does that, if the atoms go in those locations, there's actually an interaction energy between the dislocation and the atom, and they couple like that, and they tend to hold each other in place. So that's what we end up seeing. That's the origin of solid solution strengthening, are those interactions between the dislocations and the solutes. Again, small solutes tend to sit in locations like that, and because these opposite stresses attract, and large substitutional atoms will sit at locations like that, and that reduces the total strain energy of the system, and it creates an attraction between this dislocation line and these solutes. So extra stress is required to move the dislocation away. So this is what we end up seeing. For example, if we take copper and start adding nickel, and this is at the same grain size and everything else, you can see as we go up to about 50% nickel, our yield strength is going from about 80 megapascals to 150 or so megapascals. So strong effects, and these things are very soluble in each other. And if you kept kind of going out here to 100% nickel, what do you think would happen? If you go to 100% nickel, it's pure again. So probably what you're going to see happening is something symmetric and be going down like that. It may not have quite the same location anymore. So this is yield strength. Remember, yield strength is where things just started to go noticeable permanent deformation. Tensile strength, recall from last time, is equal to F is equal to maximum stress over maximum force carried over the original cross-sectional area, greater than the yield strength, but the same trend persists. Okay, we'll keep going with that. The third strategy we can do is what we call same meaning as work hardening or strain hardening, and that's the idea that we just keep deforming the material as we end up, and in this case, the obstacle is other dislocations. Remember, we've already done now grain boundaries, solutes, and now the obstacles are other dislocations. So if we take a material and keep deforming it, it turns out you're going to have more and more dislocations that are created. They end up interacting with one another, and that ends up increasing the strength of the material. So the strength increases due to dislocation interactions. So here again is a stress strain curve like we talked about last time. Stress, strain. This would be the elastic part characterized by the elastic modulus. And here's a material with small strain hardening. It yields, and its strength doesn't change much as you put additional strain in. Most materials look more like this, whereas you put more and more strain in, the strength increases because the dislocation density increases. And if you're to unload and reload, you'd go back up along this elastic line, again showing that elastic and plastic are fundamentally different sorts of properties. So if we're going to do some kind of an operation where we intentionally change the shape of something, we can quantify the amount of cold work we put into a material, and this is equal to the change in area, the original cross-sectional area minus the deformed cross-sectional area divided by original times 100 gives you an amount of cold working that you can put in a material. You can quantify that. So this is done all the time. This is done in forging, wire drawing, rolling. I've talked about before. You change grain shape as well. Extrusion is, if you look at the chalkboard tray that you have in your classroom, that's a good example of extrusion. All of these things put in massive amounts of cold work and end up increasing the strength. So forging is basically you take a piece of metal. This can be done hot or cold. You clamp it between some very hard steel dies. You make a shape that way. Drawing is the way we make wire. There's some great ASM demos of using drawing plates to take wire of one cross section, reduce it to a new cross section. You can see that those wires get stronger and stronger as you put more and more cold work into them. And next thing you do is rolling. We've talked about a little bit. Original cross-sectional area, final. And then, like I say, extrusion is to me kind of a magical process with aluminum. You can just take this and take solid aluminum, squeeze it through a die that can have some kind of a very complicated cross-section associated with it. And this is where you can make things like window frames and chalkboard trays and automotive parts and all kinds of cool things. You can get a lot of shape for a small amount of money with these extrusion processes. So the origin of strain hardening is the following. There's sort of a compressive state above the dislocation, a tensile state below it, and basically if these areas of compression tend to repel one another, so these like dislocations repel, and these areas basically give you extra lattice strain energy. And opposite dislocations attract. For example, if you have these two dislocation lines, measures an extra half plane down here, extra half plane up here. If these come together, this moves over here, you could imagine that these come together forming a continuous plane, and that goes away entirely and you lose the crystal defect fully, and that indeed happens all the time. So these opposite dislocations can attract, these can overlap, can actually annihilate the extra half planes. But the important thing is these put forces on each other. There's all kinds of ways dislocations can immobilize one another, and that's one of the strong origins of strain hardening. So this is what you see during cold working. Dislocations entangle with one another. They become cold worked. More dislocations generated as you put more and more cold work in, and dislocation becomes more difficult. We can also measure dislocation density. Engineers usually aren't creative people. Usually for density we use rho. We use it for physical density, grams per cc. We also use it for dislocation density. And usually that can be shown as line length per volume. It can also sometimes be seen as number of intercepts per area. In either case, the units are length to the -2, for example, number of dislocations per square centimeter, or square millimeter, or square micron, for example. But you have massive amounts. You can have miles of dislocation density in a square centimeter of material, just massive amounts. They interact with one another, and that can give you tremendous strength. So here's again the impact of cold working. This is, imagine taking a piece of copper. Without cold work, you might get a stress strain curve that looks like this. Put in 4% cold work, you can see the yield strength increases quite a bit. The tensile strength also increases somewhat. And put in more cold work, yield strength increases further. Tensile strength increases even further. So there's a bunch of problems you can do with this. What you end up seeing, here's yield strength is a function of cold work. Copper is pure. Brass is an alloy, therefore it's stronger. 1040 steel is 0.4% carbon, even stronger yet for a bunch of reasons. But all of them, as you put more and more cold work, the strength goes up. We also see the ductility decreases as a function as you put more and more cold work in, and you can see that as materials get stronger, they tend to get less and less ductile, meaning you get more and more um, you get less and less strain you can put in before something's going to fail. So usually you can plot, if you plot strength on one axis, ductility on another, you get some sort of a plot like that. So you could say, okay, here's a problem, produce copper bar with a yield strength over 200 megapascals and elongation over 15%. You might need that for some sort of a part. So what you could see is to get 200 megapascal yield strength, well, it looks like you need at least about 15% cold work to get that. If I need 15% elongation, you can see here's my ductility, here's 15%. This is copper here. You can see it's get about 20% deformation. So if you're put more than 20% cold work in, your elongation is too low. If you don't put enough in, your strength is too low. So the design guideline to solve this particular problem, you'd say you need 15 to 20%. You need 15 to 20% cold work. If you put in too little cold work, strength's too low, put in too much cold work, and the ductility is too low. Okay, the fourth strategy we can use is precipitation hardening. And this goes back to phase diagrams we've used before. Again, this is temperature. For example, this is percent copper for an aluminum system. You see something like this. This would be alpha. This would be alpha plus theta, for example. What we can do is hold into this range, drop down very fast, come up and hold at some intermediate temperature, and this would be, this would be alpha plus liquid up here. Alpha plus theta. You get these other particles, these theta particles that come up. And if you can make a whole bunch of these little particles, they can also interact with dislocations very effectively. Dislocation comes along, and it can do one of two things. From the side view, if it's a small dislocation, it can pass right through it and shear it. If it's big enough, it can't be sheared, and the dislocations have to loop around it like this. This is a side view. This is a top view. And the result we end up seeing is that the strength goes as about 1 over S, where S is this interparticle spacing. So if we can make a closely spaced, impenetrable particles, that gives us something that's actually very, very strong. And this is a simulation. Unfortunately, I've lost the movie. This is, you can imagine dislocation as a force that comes up like this. As this moves along through, you see that the dislocation kind of gets stuck on these bigger particles. It might miss some of the smaller ones, and it tries to move along, and it gets pinned by each of these little interactions as it moves out forward. And this is, again, very, very commonly used. This is what almost all important aerospace alloys in the airplanes you fly in are made out of, are basically age-hardened aluminum alloys. Very, very important systems. So again, this is wing material in Boeing and most other aircraft. There's now basically carbon reinforced polymer airplanes that are coming out, but aluminum is much more common. Alcoa will tell you that you can make cheaper, better airplanes out of aluminum still, and this is sort of what the structure looks like. So you get all those fine precipitates in there, and those really make it difficult for the dislocations to move. Therefore, the material is very strong. And again, we have this conundrum sort of where we can. Okay, let me go back. So those are the four methods. Just in summary, how do we make a material strong? One, we can have grain size. Small grains give you strong material. Secondly, we can use solutes. Thirdly, we can use cold working. And fourthly, we can use precipitation hardening. In each case, we're using some kind of a strategy to make it difficult for dislocations to move. Grains, solute atoms, other dislocations, or precipitates. A common problem we have is whenever you make it so that it's very hard to move dislocations, the material will tend to become more brittle, meaning you can't stretch it very far before it breaks. We'd like to be able to restore that, and we're going to talk mostly about how we restore that with cold working involved. So to restore ductility, we can do something called a heat treatment or an annealing treatment, and this is going to reduce the tensile strength and restore the ductility. So what this is really doing is reversing the effects of cold work, and so this is what you see is tensile strength shown here, ductility shown here is a function of the annealing temperature you put in. And we see that there are three stages to this that I'm going to define for you. One is recovery, next one is recrystallization, finally is grain growth. So what recovery is basically you're not making new grains, but you're basically softening the grains that you have by reducing the dislocation density within it. You put more temperature in, you get recrystallization. Should be clear what it means. Recrystallization, new crystals are being formed, and you see new crystals being born out of old ones. And that will cause your tensile strength to decrease because you're making new grains that don't have very high dislocation density in them, but your ductility increases quite a bit. Keep putting even more temperature into this, you end up getting grain growth. What you're seeing is your tensile strength is going to continue to decrease somewhat. Your ductility doesn't end up increasing very much anymore, so you're mostly just losing strength through this grain growth process. So I'll be pretty brief about this. So recovery is basically you put in some heat, you allow diffusion to happen, atoms can move around, can allow dislocations to shuffle, they can end up basically having atoms diffuse around and recovering some of those dislocations and annihilating many of them by a number of mechanisms. I'm not going to talk about the mechanisms. It's important that diffusion enables atom motion, and that will allow loss of dislocations. Recrystallization is the other thing that can happen, and what you have is you've usually got little regions in a cold work material that have very high energy density. That energy can manifest itself in the formation of new grains. And here you see new grains that are starting to form. Those new grains will nucleate and grow, run up against each other, and you can see this is after 3 seconds at a modest temperature in, I believe this is a brass alloy that you end up seeing here. And that's recrystallization, formation of brand new crystals. They can be very small. And you can see this is a little more time comes in. The material isn't fully recrystallized after 8 seconds. It's almost fully recrystallized. You see these very, very small grains that have happened. So because you've replaced heavily cold work material with soft material, the strength goes down quite a bit, but the ductility goes up quite a bit. And then the last thing you end up seeing is grain growth. And if you put even more time and temperature in, those crystals grow to larger and larger sizes. And that ends up causing the strength to further decrease. Doesn't do much with ductility. Let's not worry about that. It's a bit too advanced. So that's basically the summary of this. Dislocations are really important in understanding the mechanical strength of metals and alloys. Making dislocation motion difficult is the key to increasing strength. And we have a number of strategies, including decreasing grain size, adding solid solution impurities, adding second phase particles, cold work, and we can reverse the effects of cold working by annealing. So these are the primary tools that we use to make the high strength materials that our society runs on, things like airplanes, automobiles, beverage cans, bullets, armor, all these things that we know and sometimes love. So that's basically it. We'll be back soon talking about how this fits together in the context of some bigger picture things is where we're going to go next. And look forward to hearing from you online and such. Bye.